you are into range and performance. Well, it is very difficult to make a model or a demonstration for range and endurance and performance parameters like landing and whatever, like maneuver and things like that. But professor had intuitively punched me that if you can come with small demo of each thing, that will be really good for the class. So from that day onwards, I was thinking, what do we do for the range and endurance? All of you have heard of drag, and all of you have heard of induced drag. He has already introduced that to you. So if we reduce drag, naturally our performance should improve. In this case, I am trying to reduce induced drag. How do I reduce induced drag? Ludwig Prandtl was the first one who thought over mathematically the elliptical lift distribution, and thereafter it was Lancaster, if I am right, who came out with it. So this was my last experiment. This time I have been a little more professional. I marked the center position, and then I have been a little more, I have added a little more perfection into it. So you will find them behaving much better than the earlier ones. So they will go in their own way. Basically, I am trying to look at something which, okay, so this was the last. Now what I did is I gave an elliptical cut. So I just thought probably I'll try it out, and the results are visible in front of you. Okay, there is a small probably disturbance. If I do it like this, then it takes a more. As you vary the CG a little further or adjust it, then, and the final wow was with this one, small one. I think it does the same thing as it did at home. So elliptical lift distribution, elliptical distribution does affect the performance of the lift. I mean, it reduces the drag, and it does affect the performance. I just wanted to show it to you. And with Sir's grace, the first in-camp paper was on this. That's all. Thanks.
Yeah.
Good afternoon, sir.
Start timing.
My name is Anjali Singh. This is my team right wing.
Now onwards, 10 minutes first bell, 15 minutes you have to stop, 5 minutes for question and answer. And I don't know if it leads to 20 minutes. I don't know. You should say so. Because 10 minutes is presentation. 5 minutes for question answer. If they lead into question answer, then there will be no question answer.
Right.
So.
Good afternoon, everybody. My name is Anjali Singh. This is my team right wing. So I'm here to present optimal speed and maximum range and endurance force and drag polar. So let's first recall what is endurance and range. So for different kind of aircraft like jet and propeller, for jet to maximize the time in the air, we need to minimize the rate of fuel consumption, which means flying at the speed that produce minimum drag. This occurs at the maximum lift to drag ratio. If we talk about the range in jet, to travel the further distance, we need to distance covered per unit of fuel. Okay, speed and drag. The ideal condition is flying speed that minimize the drag. Okay, let's move to the propeller endurance. Maximum endurance is achieved by flying at the speed of minimum power required. And for propeller range, maximum range is achieved by flying in the speed of maximum lift to drag ratio. While we are doing this calculation, we have like most of assumptions. So what assumptions we are making are, first we are assuming that the flight is steady, and the second, the constant weight of the aircraft. The other is, there is one constant we take like 1 upon that aircraft ratio kind of. We are taking it as a constant here. The other is constant atmospheric conditions. We are assuming that air density is constant here. specific fuel consumption, and constant efficiency, which you further see in the like next slides. We have lots of derivations, or how we are driving the polar drag parabolic kind of plot. These are assumptions we are making for that.
Moving on to steady level flight. So steady means unaccelerated flight, and level implies constant altitude. So the aircraft is here treated as a point mass with 4 forces, and the 4 forces are lift, drag, thrust, and weight. So the reason why the aircraft is treated as a point mass is so that we are only interested in the translational force balance and not much of the rotational one. And we are also considering trimmed aircraft, which means that the control surfaces are fixed in such a way to enable a certain flight condition. Here it is steady level flight. So when we are considering the vertical equilibrium, we obtain lift is equal to weight, and similarly for horizontal equilibrium, we get thrust is equal to drag. Anjali.
Anjali VV.
Good afternoon, everyone. I'm Vaishnavi. So coming to drag polar, the total drag on an aircraft is defined as the sum of skin friction drag, pressure drag, wave drag, and lift-induced drag. So the pressure drag involves both form drag and interference drag. And wave drag is only involved when it is a transonic or supersonic regime. But here we are considering only subsonic regime. So we will be considering skin friction drag, pressure drag, and lift-induced drag. The sum of skin friction drag and pressure drag is considered as parasite drag. The drag coefficient is defined as the drag divided by half rho v square s, and the drag polar equation is the drag coefficient is equal to 0 lift drag coefficient plus lift induced drag coefficient. So CD is equals to CD naught plus KCL square. So when we use the equation D is equals to half rho v square SCD, and we substitute the CD equation in the CD, we'll get D is equals to half rho v square SCD naught plus KCL square. Coefficient of lift is defined as lift by half rho v square s. Since we are considering steady level flight, lift is equals to weight. So we'll substitute weight in place of lift, and when we derive it, at last we'll get drag is equals to half rho v square s CD naught plus kW square by half rho v square s. As we can see that the first term, half rho v square s CD naught, the drag is directly proportional to v square. This term we considered as parasite drag, and the second term is inversely proportional to v square. This is lift induced drag. So in this diagram we can see that the lift induced drag is inversely proportional to v square, and the parasitic drag is proportional to v square, and the upper curve is the total drag. And the below figure represents the drag polar. This drag polar is for a symmetric airfoil for in subsonic regime. Here we can see that the curve where it intersects the CD axis is the point is CD naught, that is 0 lift drag coefficient. Moving forward, the middle graph is for positive cambered airfoil. We can see that the drag polar has shifted upwards, and the point where it intersects the CD will be CD naught, and the point where the CL at minimum drag is CD minimum. Here CD minimum is not equal to CD naught because for a positive cambered airfoil, CL is 0 at a negative angle of attack. So when it is at a negative angle of attack, there will be more skin friction drag, and the pressure distribution above that airfoil is such that the pressure drag is also more when compared to when it is at a positive angle of attack. So this is the reason why CD minimum is less than the CD naught. And the other inferences which we get from a drag polar is each point at a drag polar on the drag polar defines at a particular angle of attack. So when we draw a tangent to the drag polar from the origin, we'll get the point for maximum LYD, maximum lift to drag ratio. For a parabolic drag polar for a wing with positive camber, the drag polar is defined as CD is equals to CD naught plus K CL minus CL naught whole square.
Good afternoon, everyone. Myself Navya. Today I will explain you the range derivation. Usually we know that range is defined as the maximum distance traveled by the aircraft during one load of fuel. How it was derived from the very basic. Like we know that velocity is equal to distance per time or displacement per time when we take the magnitude and all. So range was given as integral VDT and F dot is the fuel consumption per unit time and all. So R can be written as integral V by F dot dF. Now R, the maximum range will be maximum when V by F dot will be maximum. So V by F dot is nothing but the distance per unit fuel to be maximum. For steady and level flight, we made an assumption that thrust is equal to drag and lift is equal to weight. For aircraft, we choose as jet. We have that F dot is equal to CT, where that small c represents the specific fuel consumption. And now F dot is equal to CD. From steady and level flight, we can write T as D. Now, V by F dot can be written as V by CD. Here is the keynote, like when R has to be maximum, that is when V by F dot has to be maximum, which results in D by V minimum. So, to obtain the optimal speed for maximum range, the condition was D by V minimum. So, the corresponding velocity is this. Vm d by v is equal to 2 by rho w by s into under root 3k by cd naught, where rho is the density, w is the weight, where s is the wing area, and k is the proportionality constant of induced drag coefficient. Cd naught is the parasite drag. I will show the derivation also. After that, for aircraft which uses piston prop, the condition will goes like this. For maximum range to be obtained, the drag, the velocity to be derived should have a minimum drag, and the corresponding velocity is this. And for each and every velocity, like the conditions like d by v minimum and d minimum, it has follows like this, like velocity, cd naught, cl, cd. The conditions are related like this. Now I'll show you the derivations. Now, we'll start with the force balanced case. So thrust was equal to drag and lift is equal to weight. We can rearrange the equation like thrust is equal to weight by L by D. And in the non-dimensionalized form, L by D can be written as CL by CD. L by D is also called as aerodynamic efficiency. And now, our goal is to get the minimum drag. So the drag minimum can be obtained at L by D maximum. We know that drag is equal to half rho V square S is CD. And CD, just now she explained that how we got the drag polar equation, that is CD is equal to CD naught plus KCL square. I just substitute everything in the equation and arranged in such a way that to obtain equation like this. Drag is equal to K1 V square plus K2 by V square. That is, drag is only a function of velocity. Only a function of velocity. And K1 is CD naught half rho S and K2 is KW by half rho S. Now, to obtain the drag minimum, since it is a function of only the velocity, I have to do the differentiation. We know that differentiation to be done to get the maximum or minimum value. So that when I did the differentiation, I got a condition like this. V minimum drag is equal to K2 by K1 whole to the power 1 by 4. When I substitute K2 and K1 value which I had here, we will be arriving to the velocity this. So this is the optimal speed that has to be for optimal range for jet. And now for this is for drag to velocity condition. So this is the key equation which we derived in the last case. This can be used for minimum drag to velocity condition. The previous one which I shown was for drag minimum condition. So when we are substituting it and making it a function of V alone and doing the derivation to get a condition like this and substituting the values. And the relationship between the V minimum d by V and the V minimum drag was 3 whole to the power 1 by 4. Now how the endurance was done will be explained by fellow teammate.
Good afternoon everyone, I'm Karthik and let's look at maximum endurance, the velocity corresponding to maximum endurance. I've listed down the required equations or required conditions on the top. maximum endurance can be calculated from the weight flow rate being equal from the weight flow rate formula itself. We can write W dot as dW by dt, and integrating dt from from initial to final condition will give us the total time taken for the flight. That is the endurance. And for turbojet, we've written dW by dt is equal to minus Ct into T. And from steady level flight, writing thrust as drag and including lift also, we get the formula for E as follows: 1 by Ct, Cl by Cd, and in terms of ln. For this maximum condition, we see that Cl by Cd needs to be max, which again goes back to same mathematical derivative being d by dCl of that condition. Cl by Cd should be 0, which gives us Cl is equal to Cd naught by K. Writing that, substituting this Cl in for velocity from the Cl equation, we get V infinity is equal to 2W by rho infinity S under root K by Cd naught. Similarly, if we write the same for a turboprop, we get W dot is equal to C into P instead of C into T, because propeller aircraft needs power. Similarly, writing we obtained the equation doing this almost similar mathematics, and that for again the E maximum condition, we get d by dCl of Cl power 3 by 2 by Cd is equal to 0, which gives us a Cl condition of under root 3 Cd naught by K. Substituting it gives us this following velocity condition. One interesting thing to note is that, as given by the graphs from Anderson's aircraft performance and design textbook, we see that the V infinity for best endurance for a propeller aircraft is less than the V infinity for best endurance for jet aircraft, and that relation is V1 is equal to 0.76 of V2, V1 being for propeller, V2 being for jet. Similarly, it is also given for range as well. And one other thing to note is that there is no effect of wind on the maximum endurance as given given the textbook itself, because range depends on the speed covered on the ground with respect to the ground, but endurance depends only on the relative speed of the aircraft and relative speed of the wind with respect to the aircraft.
Good afternoon, everyone. I am Tarishi, and I'll be talking about the limitations due to the theoretical assumptions that we took in the beginning versus the actual reality, as we considered to be a constant weight, but the weight changes as the fuel burns. So the optimal speed also decreases with the lighter aircraft. And the second thing is an interesting thing that companies like Airbus uses is a cost index, which is time cost upon fuel cost. They use it to use it according to the mission requirements to compare between if the time is more important or the cost is more important. And also, if we use a low range cruise speed, like by reducing it, by increasing the fuel burn by 1%, we can get a gain of 3 to 5% of a speed. And there is also headwind and tailwind effects which we have not considered. And also the ATC requires for the aircraft to fly at a constant altitude, but the curve shows that it's a constant cruise climb, but so step climbs are taken into account. And also at high altitudes the margins are pretty low, so a safe margin has to be maintained by the pilots. And thank you.
Do we have time for questions?
No, last 2 minutes, 3 minutes more than 15.
Okay, fine. Thank you.
Mike, start. Mike.
Start, sir. Good afternoon, everyone. We are Team Turbulence Squad. I am Gaurav Datta. So we will be presenting today that why do we have an optimal speed for a maximum range and endurance of an aircraft from the perspective of energy, height, and specific excess power. So just to give an idea, I mean, it's a very easy way to see that energy is basically one metric to explain that one. And we know that whatever energy my aircraft is flying into is coming from the burning of the fuel. So at the end of the day, whatever the energy is being released due to the burning of the fuel is getting stored or getting basically manipulated, converted into the potential energy and the kinetic energy of the aircraft. So this effective total energy can be converted into a metric which is nothing but equivalent height, which has the potential energy contribution as well as the kinetic energy of the aircraft. And we'll see in the coming slides how this metrics can be used, as well as there is a specific excess power, how these metrics can be used to give an intuition why we have a specific speed, an optimal speed for both endurance and range, and they will be different. So that will be covered in the next, coming slides. But here the intuition is that this is a metric which will give more intuition towards that. And as we can see, we can have the same energy in terms of the energy height at two different flying conditions. For example, we may be at a lower altitude, but it will be having higher velocity, and then going up. So it's a trade-off. So we can exchange energy at a given energy. There are graphs which explain that, which will come in the which will be there in the coming slides. And the same thing which I was trying to say that at a given, these curves are the locus of constant energy height, and we can trade off. So at this particular energy height, maintaining the energy height, we can trade off between the kinetic energy and the potential energy. So the pilot can effectively use that as a driver. And this can be easily understood by the fact that there is one concept called the specific excess power, and that actually gives us a understanding about the values available with the pilot while he is flying. So for example, this is basically the instantaneous rate of change of this energy height, what I explained above. And if this PS is positive, that means the aircraft, the system has energy so that it can go to the higher energy state, the energy height. If PS is negative, it has to come down to the lower energy state. And we'll see that in the coming slides how PS has to be 0 for deriving the optimal speed for both max range and endurance. My next teammate will explain further.
So my name is Yash Patel, and this is the energy landscape where we can see from the altitude versus velocity graph that this is the whole region where our aircraft is flying. These are the different types of the specific energy balance. So if this is C1 has a higher energy, and as we go upward, it will become a 0. So that's the point where all the specific excess power will be a 0. So we'll try to see that how it will be affect if I want to go from a 0 to Mach 2 with a higher range and without using so much fuel. So starting with the step 1, where when we are climbing as a climbing in a subsonic region. So what we are trying to do this. First of all, we gain some velocity by whatever the energy we have in the form of fuel. So from 0 to let's say 450 or 440, we can accelerate our aircraft, and that acceleration convert the specific height. By using the specific height, we can convert this to altitude. So from this we can go to the C1 and the C at the above of the C2, where we have the specific energy which is lower than the maximum which is here. At this region, we are just near at the transonic region. In transonic region, we know that there are the wave drag which are the dominant part. So if we are accelerating more in a wave drag, so we are losing the much important, which is the fuel. So we have to optimize fuel, and also we have to still go to Mach 2. So what we do, say in a transonic zone, we reduce our altitude and gain acceleration. So while diving also we are increasing the specific height, and when we achieve that Mach 1, Mach 2, Mach 1 above Mach 1 velocity, then after that we convert this energy to that particular altitude so that we can reach Mach 2. So in a single line we can say that there is one शायर called that दुनिया झुकती है झुकाने वाली चाहिए. So झुकाने वाले काम ये ट्रांसोनिक करता है आपका. Yes. Yeah, and this is the final formulation where it's given by Rutowski. So it's not like a budget equation where they are using V by T, but here what we have a simplified version of the equation, where these are the terms where dominant are range. So what we can do, as my aircraft is moving, so its weight will increase, is also increasing our range. We have a specific heat which also increasing our range, which is a propulsion energy which also increasing, and the L/D ratio. So there is one case study we have taken, that why at a Mach 2 the range will drop, because the fuel is unchanged. The whatever propulsion we are using, its efficiency is unchanged, and more or less our structure is also unchanged. It's not like that at the altitude we are adding some structure and all. So the major dominant part is the L/D part, where it significantly dropped due to drag increase. So the one of the crucial thing is, whenever we design, whatever we do with our geometry, aerodynamic geometry, but still we require that fuel that will enhance the range. Yes. Thank you.
Myself Adarsh. Now we'll talk about what is endurance. As endurance is the time that an airplane flies with a full charge of tank. Its unit is time, so can be measured in second, minutes, and or hours. It is mainly applied in those conditions whenever an airplane or drone used to do surveillance work. So in those conditions, it moves around a constant height, and we needed to maintain it a longer duration of time to do the surveillance. Now, suppose W0 is the total weight of airplane. W1 is the weight of airplane without fuel. So weight of fuel will be W1 minus W0. Now we'll define a parameter CT, which is the rate of weight of fuel decreased per unit thrust. So CT will be minus dW by dt divided by TA. So we can get dW is equal to minus CT TA dt. And now from that we can get the expression of dt as dW by CT TA negative sign. Here we can integrate this in form of W to get the time. So at time t is equal to 0, we have full weight, which is W0. At time t is equal to E, which is the endurance time, we have only weight of airplane without fuel. So integrating this, we'll get a total endurance time. Now Gaurav will continue next.
Here I'll be talking about range. The range is basically the horizontal distance in ground frame that is traveled by the aircraft for a given amount of fuel, and that can be determined by the weight, the rate change of weight of the aircraft, and that is nothing but the rate change of fuel of the aircraft, and the ds by dt, that is the velocity, and that also depends on the headwind or tailwind, because the horizontal distance that is taken with respect to the ground frame. The next part, design consideration will be talked by Nirav.
My name is Nirav. So when we translate all these mathematics into the design considerations, we get two key considerations here. One is that we need to minimize CD in order to obtain a most efficient flight path during the flight, because CT is the inner denominator, and it is quite intuitional that why we need to minimize CD, because CT is the amount of thrust spent on unit amount of fuel spent on unit thrust. So it is quite intuitional, and when we talk about range and translate into some other variables, we see that there is rho infinity in the denominator. So we need, in order to maximize range, we need to fly at quite high altitude. That's why there's a optimal altitude which is around 30 to 40,000 feet, at which subsonic aircraft generally fly in order to maximize range, where they can get the induced drag is very low due to the rho infinity is low, but they can get sufficient lift also in order to maintain the flight. So yeah, that's all the key considerations here. Next, Somik will continue.
Good afternoon, everyone. I'm Shomik. So the mathematical parts have been explained by my fellow teammates. I'll be going for the graphical interpretations. And here we have the graph of energy height versus airspeed. At energy height, these are the constant energy heights. As you can see there, lines of constant total specific energy or height. And in the second plot, we have the PS equal to 0 regime. In the PS greater than 0 regime, we have excess power available, while in the region outside, we have PS less than 0, where there will be less power than required, and hence there will be a descent. And then we have this curve of specific excess power versus speed. This is the PS equal to 0 envelope, and at these points where the given points for maximum endurance and maximum range, those ratios and conditions have been set by my teammates already. And at these points, there will be those CL by CD ratios, and the velocity at which we have the maximum range is around 1.32 times the velocity at which we have the maximum endurance. So from this, my teammates will. This plot is derived from the previous plot. So it can be seen that PS is equal to 0 line like has 2 points where we can get. So one corresponds to max endurance and one corresponds to the max range. That is highlighted from this plot.
So hello everyone, I'm Shubham, and the next we have the power versus velocity plot. Here we can see we get an optimum velocity and for a minimum power consumption, that is the locus of the maximum endurance locus for the velocity for which we get the maximum endurance. And we can see the two curves. The upper one is plotted for the heavyweight flying vehicles, and the below we can see is for the lightweight aircrafts. And next, this is the max range locus. Here we have seen for the thrust versus velocity plot, the max range points denotes the tangent points on the locus, and again for the above graph is for the heavyweight vehicles, and the lower one is for the lightweight vehicles. And next, Bharat would like to finish it off.
Yeah. Even though we are considering every parameters in the theory, there are some limitations. So we are comparing theory versus reality here. You can see the EM theory prediction and the real world limitations. For the weight, we are considering constant weight, whereas in real world limitations, we have weight constantly decreasing because of the fuel flow. And engine, we are considering thrust available as a one parameter, whereas in the real world life, fuel flow is varies with RPM, temperature, and also different gust winds and disturbance varies with that. Environment, we are considering like standard atmosphere, basically which is available as a standard atmosphere. We consider that one. But in a real world case, there are weather changes and also wind and non-standard atmosphere temperature changes and all. And for airframe, we are considering infinite strength for the theory calculations, whereas in the real world cases we have Mach limitations and also structural G loads, which can affect the structure of the airplane. Thank you.
Oh, 1.5 minutes is left.
Yeah.
I'll do something quick. Serious. I just want you to tell me, in a ordinary situation, where do you find endurance?
So I can give one situation, but it is not really moving. I mean, for example, I can give an example for a bike. Suppose I have 1 liter fuel and I have same bike in 2 cases.
Like we have an event yesterday night from 2 days. So there was a drone capturing all the video recorded. It will be an example of endurance.
Sir, any surveillance, for example.
Surveillance.
In your life, it becomes an experience.
Yes.
Can we class think of loitering during?
Any surveillance or recognize.
Question is that in your normal day-to-day flying, I mean, like you are, let us say you're sitting on a aircraft going to some other place, where do you really feel the pinch of endurance?
Okay, while landing, it has to continuously wait for its turn to land
Due to air traffic.
So that is why it has to spend.
Thank you. Please don't laugh, sir. It is a fact. If I show you those pages, you will So I want to tell them Please, next we will give you 2 more days. Next Wednesday presentation. Today's presentation. Don't give it like that. If you permit me, I want to give a chance.
Good afternoon, everyone. We are Puṣpak pioneers, and our topic is the common topic is why does aircraft has an optimal speed for maximum range and endurance, and in that the subtopic is Breguet equation. So it's a more of a mathematical take, and what we'll be presenting is the derivations, because the objective written itself was concept and derivation. So we have focused on derivations. So Breguet equation for the range, endurance, and then what should be the optimal speed for the maximum range, maximum endurance, and then are there any clashes, and what exactly is the usual thing which happens in real life. So my teammate Maiko will be presenting now.
Hello, sir. I'm Maiko. So before I begin, so I'll just like to mention that this slide was created by our teammate Bhagishri, but unfortunately she couldn't be here today, so I'll be presenting on her behalf. So yeah, so an aircraft's performance is affected by various parameters, whether it be the fuel on board, whether it be the aerodynamic efficiency, the mission requirement, the fuel combustion efficiency, the mission requirements. So this is what we'll be looking about in this our presentation. So the just to briefly mention that the range is the total horizontal distance flown by the aircraft, and the endurance is the total time the aircraft can remain airborne. And we seek to optimize for this and get a optimum speed so that we can maximize the range and the endurance. So we will now begin the mathematical analysis for this. So my teammate will now go ahead with that.
I'll just go through the derivation of the range. So range is the total horizontal distance flown by aircraft for a given fuel. So to derive the range, like it depends on the aircraft, if it is jet or propeller. So here CT and CR or CP are specific fuel consumptions. Specific fuel consumption depends, like it can be derived based on thrust or per unit power. So it depends on the aircraft. So for the jet, it depends, like specific fuel consumption is defined on thrust because it burns fuel to produce thrust. So from there, like we can get WF. So this is the derivation. So so by equating the balancing equations from the on a level flight, so T is equal to drag and thrust is equal to drag, and from there we can derive like T is equal to W by L by D. So from there we can get this, and then after for D we can define range dr is equal to vdt. So by solving those both equations, we can equate to this, and same in the propeller aircraft also. So next is endurance. So Pragya will take over.
So, like Harika said, that range is the horizontal distance covered for a given amount of fuel. Endurance is measured in units of time. So that how much time the aircraft is in airborne situation. So there are two separate things. One jet aircraft and other is propeller aircraft. For jet aircraft, we will equate. For jet aircraft, we use thrust specific fuel consumption, in which we use the equilibrium equations, and using that we derive it for steady flight condition, and this is the derivation. And for propeller aircraft, we use power specific fuel consumption, and shall I explain this?
If you have the time.
Okay, so this is the change in weight, derivative of weight with respect to time will be given by is proportional to the thrust, and using this equation we will equate thrust with weight and L by D ratio. And now we will integrate time to get the endurance for jet aircraft, and this is the final expression for endurance of jet. And for propeller, we use a drag force majorly to get the power required, And with that power required, we integrate with respect to time again. So we get this expression. Now, Apur will cover the next topic.
Okay, so if we look at the optimal speed for jet aircrafts for corresponding to the maximum range, we can derive it straight from the Breguet's range equation. First, we will look at the minimum drag speed. Drag is a combination of the parasitic and the induced drag. And if we write the drag in terms of velocity, if we look at the parasitic drag equation and the induced drag equation, these can be written in terms of velocity of the aircraft. Thereby, if we minimize the drag equation with respect to velocity, this will give us the minimum drag, the velocity corresponding to the minimum drag, which we get as the expression written there. So as per the that expression, the minimum drag velocity corresponds to the one where the parasitic drag equals the induced drag. And from the Breguet's range equation for jet aircrafts, we see it explicitly depends upon the product V times L by D ratio, and which is proportional to under root CL by CD. Thus, if we minimize this factor with respect to coefficient of lift, we see that the maximum range condition corresponds to parasitic drag coefficient equals 3 times K lift coefficient square, where K is 1 upon pi E aspect ratio, where E is the Ostwald's factor for the wing. So this implies that the maximum range speed is actually equal to somewhere around 1.316 times the minimum drag speed. Now, in this derivations, what we considered is that the lift by drag ratio remains constant throughout the flight, but as it burns fuel, the weight of the aircraft decreases, and therefore lift decreases as well. But if we look at the coefficient of lift equation, CL equals L upon half rho V square C. If the lift, to maintain a constant CL, what we require is the density must reduce continuously throughout the flight. Hence, the aircraft must gain altitude continuously throughout the flight duration. But this is not realistically possible due to some ATC restriction. But in long distance flight, what pilots do is something called stair stepping, where they increase altitude in phases in the low traffic region, therefore to maintain the constant maximum range velocity of the aircraft. Next, for propeller planes, the range equation depends explicitly on L by D. There's no velocity term in there. Hence, the maximum range velocity corresponds to the condition where the parasitic drag is equal to the lift coefficient, K lift coefficient square, which is same as the minimum drag velocity that we saw in the previous slide. But for propeller airplanes, the minimum drag velocity is considerably lower than the max velocity of the aircraft. This would mean a significantly longer flight duration. Hence, an aerodynamicist named Carson, I forgot where he was from, but he considered that minimizing the weight of fuel consumed per unit velocity would actually give us the optimum flight velocity, thereby giving us a trade-off between economy and flight speed. And this would give us a optimum flight speed of around 1.32 times the minimum drag, which is called the Carson speed relation. Hence, for propeller airplane, this is the most optimum flight velocity not the minimum drag, although we get the one from the range equation. And if we look at those curves, the being slightly off the minimum drag velocity is not as bad as inefficient as we think, because these curves have nearly flat peaks at low velocity, at maximum velocity.
Good afternoon, everyone. Myself Bhavika, and I'll be explaining the optimal speed required for endurance. Endurance, it means that total time aloft that corresponds to minimizing the fuel flow rate. So we have taken both the jet and propeller. So in jet, we can see that the speed term doesn't explicitly appears. So we take the L by D ratio, which is maximizing the CL by CD. So on maximizing CL by CD, we have the drag polar, which is the equation, and we differentiate with respect to CL. We differentiate with respect to CL because choosing a CL corresponds to fixing a particular velocity. Because for a given aircraft, for a given altitude and a weight, in every steady level flight, there is exactly one CL. And if we differentiate it with respect to V, it will give us a very rigorous and cumbersome algebra because it is a V square term. So when we differentiate with CL, the CL we get is that CL which corresponds to the optimal speed at which the jet aircrafts fly with maximum endurance. So from the lift equilibrium, we have the expression for V, and we substitute that CL into that expression, and we get the optimal speed for jet. Similarly, the same steps is the same procedure is used for propeller jets, but propeller we maximize CL 3 by 2 raised power 3 by 2 by CD ratio, because the propeller driven aircrafts, the fuel flow rate depends on the power required. So so on this with the same process, we get the velocity for optimal velocity for propeller driven aircraft. Now I'll ask Shruti.
Okay, so this is the summary of whatever we have discussed. Most of the things which we are discussing has already been covered in the previous slides. Okay, so this is the summary. So for propeller and jet, as it is told, because propeller is driven by power, which is required to run the shaft, but jet it is driven by the specific the engine. So obviously the the expressions are different, and what we get is for maximum range, we'll get maximum range as at L by D maximum, which also corresponds to the maximum endurance for the jet case. So for the L by D maximum, we'll get a minimum drag from the drag polar, VMD. So we are representing that as VMD. So for maximum range, we'll get VMD, but for jet, we'll get a velocity which is higher velocity than VMD. That means without minimizing drag is not the if you want to maximize range, intuitively it will feel like maybe if we minimize drag we go farther, but this is a bit counterintuitive, that we have to get faster, we have to fly faster. So that is for jet. And then for endurance, if we see where minimum drag is not the case for the maximum endurance, it is lower, the velocity is further lower than whatever we require for the minimum drag. So why? Because for that your power requirement must be minimum, and hence for the given amount of fuel you will be able to loiter or stay afloat for a longer time for a propeller. But for a jet aircraft, endurance maximum endurance corresponds to maximum L by D, because then you are just throttling to balance it, and you will you're not wasting any excess power, so you can be aloft for a longer time. So this is the summary, and this plot is already covered in the previous presentations. So if you see the drag polar thrust, or if you can see thrust, and in this Breguet equation assumption, thrust is equal to drag, L equal to W. We are always at the steady level flight. It is ignoring the takeoff and landing phase. So minimum drag point is where you will get best range for propeller and best endurance for range. And for a lower velocity, you will get best endurance for propeller. And if you go to a higher velocity, you will get the best range for jet, which will be the Carson speed, which he told. That Carson speed is something which might not give the least maximum range, but it will optimize the fuel and time. So that is one thing. And what are the limitations? So it ignores takeoff and climb, and obviously we need to account for that also in power. Then we assume that the specific consumption is constant with respect to time. Then wind effect is not considered. If it is considered, the velocity will shift left and right based on head and tail wind. Then all these assumptions are the expressions which we are using are all for subsonic. So there's no drag divergence and all that which happens with higher Mach number. Then as weight increases, you need to adjust the altitude if you want to get the LYD max. So typically for ATC won't allow you to simply climb up. So you will just do in steps. So you will again throttle up, go up, again do in steps. Then mostly what aircrafts do, so for commercial, majorly we need to go to a higher range, but also to save time. So it will be not at the maximum range, but in between maximum range and a little high, velocity will be little higher than maximum range, so that overall fuel will be lesser. Then for fighters, it will be based on what your objective is. So during transit time, when you want to go somewhere, you will have a maximum range velocity, which will the velocity for maximum range. But for loitering and other cases, you will need maximum endurance. So accordingly, you will choose which speed to dwell to. And then for private jets, there's they don't really bother about fuel efficiency. They just want to go to places faster. So obviously, you'll dwell at maximum speed. So this is the summary for the whatever conclusions we draw from Breguet equation. And any questions?
You have 35 minutes, 35 seconds. Like, but 1.32, I want to ask you, sir. But 1.32 comes by a definite derivation. Yeah. They don't know about. Yeah. Constant speed. There is a propeller ke liye, for propeller. 1.32, there is a physics behind it. I don't remember correctly, but I remember having gone through it. These people are just washing it away by saying 1.3 aa gaya kahin se.
Yeah, they have the square root of 3 coming in, and there's a further square root.
Yeah.
So it takes care of that. We have not specifically.
Sir, I have a question.
Yeah, go ahead, please.
Can we define any range or endurance for fighter aircraft?
But most of the time it will be, it depends. That's what this whatever equations we are writing, that is just for steady level. Yes. And but fighter aircraft, this might not, because most of the time you'll be going up, doing that. Chasing and.
The agility of the aircraft.
This is more for commercial. I think this will give a good estimate. Not valid for fighter, sort of.
Can we write for fighter if it's not?
So equation, this closed form solution, this assumes a lot of things.
Yeah,
so you will not be able to get any closed form.
Can you approximate solution if it's not performing a combat that which could be missile-based? Yeah. Usually, I think we have told the right answer. It's actually based on the mission. I mean, it all depends. Suppose you want to go and fly the standoff mission. So you can define your endurance or range based on that. So
that is what is written. That for depending on but still, if you're doing a lot of chasing, and then what is the point of because so many assumptions.
Design driver for them, but design driver or something else.
You don't want maximum efficiency. You want.
No, there is something called combat radar also. Should have a range. There is range, but that is not for endurance. That is not really from the design driver. It's a performance.
For cargo.
Combat range is different. There are some different combat range that's for it. So they are different.
So you have a range from your base to the border.
Yeah.
You have a range, then you have endurance there, then you come back and you land.
Yeah. And nowadays for endurance you are having that inside refilling.
Good. Those are thought-provocative questions. This is the kind of questions I want from the audience. But if you look at it, if you want to extend it to all those additional things that the aircraft is supposed to do beyond just the cruise, then actually the starting point still remains the same, because it's the definition either of C or CT. That is what you're starting with. In this case, it's turbojet usually, so it's CT. So that definition still remains. It's just that where you're substituting the equations for lift, drag, weight, and thrust, these simplified equations, you'll have to accordingly modify for whatever is the n value for that in terms of the.
In our presentation, we wrote two equations for a range and endurance in terms of time and distance. So that is an instantaneous equation. So now,
correct.
Yeah. So once you put on the values, you can actually
exactly. Yeah.
solution, we need some.
So precisely where you are going to be modifying that is in where the velocity is in terms of CL. So that will get modified based on what exactly you're doing rather than cruise. So you'll have to accumulate all that, because even in the case of a regular commercial flight, it's not doing only the cruise. It has to taxi, it has to climb, then again it has to descend, loiter maybe, and then right. So all of that, the rate at which the fuel is consumed will be quite different. But still the starting point remains the same. That's the beauty of it. Because yours is about Breguet, I just wanted to make sure that everybody pronounces this right. The names are very important. People take offense when you're presenting in international context. Breguet is a French scientist. His great-great-grandfather was the founder of a watch company, which is like really one of the high-end watches among Swiss watches. Okay, like you would have probably heard of Rolex and things like that, but this is considered even higher level, Breguet watches. The great-great-grandson of that was an aircraft pioneer as well, and he derived this. The T is silent, so Bre and Gay. So you just think of it as two syllables. Also, again, there's always a conflict across the English channel between the French and the English in terms of how they pronounce it. The English tend to, whether they are in America or in the UK, they tend to pronounce the initial portion with a greater stress. So they would say Bre-GAY. The gay almost comes down, whereas the French want to maintain that volume, loudness in all the syllables. And so you will see for an English speaker like us, it tends to almost like the gay is actually pronounced with a higher volume. They say Breguet. That's how the French would like it to be pronounced. Okay, these are not technical things, but especially as you go forward, you'll be probably presenting in international conferences, etc. So these can become kind of distractions from your work. When you're presenting some really good quality research and then somebody is just picking up on that, they may not say it out, but their mind starts going on a tangent because of that. So see if you can avoid those things. Another beautiful thing is there's an Indian connection to that as well. All these watches essentially call it as horology, and that hora is something that even though people might think it's about hour, we have in Indian astronomy and astrology a measure of time called hora. The original comes from that hora. They say Sanskrit is the mother of all languages, and this is not something that we Indians alone say, but a lot of international historians have researched to say that. This is another example where hora comes into timing and timing comes into endurance, etc. Thank you. Also, not just your team, but I like to appreciate the previous teams as well. You're doing a pretty good job, especially in terms of the coverage, also in terms of the reduction. I can understand that larger teams are taking a little more time because you want at least a minute or minute and a half for each member. I think the best thing would be to kind of practice once before you come here, especially for the larger teams, so that you ensure that you are within the time. Another thing that I'd like to appreciate of all the three teams which presented so far is in terms of the reality checks that you're giving, talking about what you're supposed to, but also at the end, like what you're talking about in terms of the different kinds of aircraft, and also all of you are starting with assumptions and ending with limitations. That's also a nice thing, because as engineers we should be always aware of not only what we are doing, but also what it's based on, what's the logic, and when that logic fails, and therefore there are limitations. So you don't apply everything everywhere. These are things that are noticed. We will not be mentioning that because of lack of time, but I just want you to understand that we are observing all of these things. Thank you.
I just want you to teach them. I just want you to teach them two more words.
Yeah.
Should we start?
Sure. Let's start the time.
Light means it's on.
Yeah. The light is where the mic is.
Yeah.
So okay, that should be towards your mouth.
Okay. Good afternoon, sir. This is Team Garuḍā. Myself, IISc Mishra. We are going to cover the propulsion aspect of why endurance and range is there should be optimum speed for maximum range or endurance. As some of the aspects were covered, but we will go much deeper into the main propulsion aspects. Okay. So, sir, considering any level flight which is in steady state, there are three forces on that. That is aerodynamic forces, which will be lift and drag. Another will be thrust, and third one will be weight. Okay. In any steady and level flight, lift and weight will be balanced, and thrust will be balanced by the drag. Okay. So we need to have a thrust all the time. Okay. To generate the lift, which will keep the balance at all time. Okay. Now thrust will come on some energy. Okay. This energy mostly it will be in form of chemical energy of the fuel. Okay. But considering envelope of any flight, there will be always be a constraint of the quantity of fuel which can be carried. Okay. Once it comes limitation of quantity, automatically it will lead to limitation of range and endurance. Okay. Now the question is how this fuel will be invested to get maximum range or to get maximum endurance. There comes the propulsion. Okay, considering propulsion, okay, all we know that how chemical energy will be converted to thrust in case of propulsion. Considering the general equation of propulsion where thrust is equal to mass flow rate and multiplied by delta V for obviously optimal expansion case. Okay, here there are two things. Either you expand the gases a lot and get the thrust, in which case V will be more. That will be the case or concept of jet engine. Otherwise, you pump a lot or flow a lot of mass flow rate to get the required thrust, which will be a case of propeller based engine. Okay, and as we see further that propeller based engines are mainly driven by power based concept, and jet is driven by or explained by thrust based concept. So here there are two things. For jet engines, it will be thrust specific fuel consumption, that will be how much fuel flow rate is required to get 1 Newton of thrust, and propeller specific fuel consumption is used, that is how much fuel flow rate is required to get 1 unit of power. Okay, further my teammates will cover.
Okay, cost to this side, I'll try to be a bit crisp. We all know what endurance is. Some of us has already explained it. And we know for the propeller, we need power consumption to be low because power consumption is directly related to fuel consumption. So question arises, what is power? Power is thrust into velocity. What is thrust? In a steady flight, it is equal to drag. What is drag? There are two, induced as well as parasite. Therefore, there are two terms. So question arises, are we supposed to fly our flight at a low speed or a high speed? Answer is none. Because if you look at the equation, I'm not going to derive it, of course. So propulsion power is proportional in A V cube plus B divided by V. So if we go at low speed, power will increase. If we go at high speed, power will increase. So suppose if there are two American aircraft, one is going at a low speed and one is going at high speed, they both will lose fuel in a mid-flight and they will need oil. They need to nuke Venezuela. Okay. So coming back, so what velocity do we need? So instead of velocity, we need to consider another factor, and that's why how we derive is PR can be derived in terms of weight, span, density, and CD by CL ratio. And if we want to optimize our endurance, we need to optimize this part. CL divided by 3 raised to 3 by 2 divided by CD. Again, we need to differentiate it. I can't do that, but I will give you an end result that we need our induced drag to be 3 times our parasite drag. If we differentiate it, we'll get the part. Now coming to the range, I'll pass it on to Nitin.
Myself Nitin Jaiswal. I'll be covering about the range of the propeller based aircrafts. So range is basically dependent upon how fast the fuel is getting burnt. And for range to be maximum, the fuel consumption rate has to be minimum. And we see it theoretically, it basically depends on the amount of power required divided by the free stream velocity. And in order to minimize the fuel consumption rate, we have to minimize this ratio of power required by free stream velocity. And we can see from the graph that would be the point of minimum slope. And incidentally, that corresponds to the maximum ratio of the lift to drag. And that is ideally it should be, because the lift to drag ratio has to be maximum so that the fuel consumption rate becomes minimum and thereby optimizing the range of the propeller based aircraft. Thank you. Kunal will continue further.
Thank you, Nitin. So I will explain about the endurance condition for jet powered aircraft. So we can see in this graph, so we have V infinite, that is air speed in x-axis, and a drag or thrust required in y-axis. So the first one graph is for induced drag, and second one is for the parasitic drag, and this blue one is for total drag. So we get the optimum conditions at the minimum point. So for VLD max velocity, we get the drag minimum. So from this relation, we can see that if our drag is minimum, we get the LYD maximum. So if our LYD is maximum, then thrust required will be minimum. So if thrust required is minimum, then we can get the endurance maximum. So this is the main concept for the maximum endurance of the jet-powered aircraft.
So can you explain the graph? Why the zero lift here?
This one?
Question.
This one?
Black curve. Why it start from zero and the other one is not?
This one? Yeah.
Yeah. Why it start from zero? Why it is other one? The lift induced here, the graph.
Yeah.
Why does it?
So that is a function of square of velocity, sir. So parasitic drag is a function of the square of the velocity. So this will start from zero. So I will write C.
So now coming to the range of a jet-powered aircraft. So if we take the same definition of thrust-specific fuel consumption, and if we resolve the time into velocity and time, we'll get this expression. So this expression basically says, if you want a maximum range, so intuitively you have to consume less fuel per mile of travel. So if you are consuming less fuel, like less mass of fuel per mile of travel, so from the equation you have to say, see, this TSFC is a function of engine you are using, so it is fixed. So your TA by V infinity should be minimum. So if the TA by V infinity, if we go to the TR, the thrust required, so thrust available, thrust required is same in the steady level flight, which we are assuming for this derivation or consideration. So if you go to thrust required versus V infinity graph, and if you plot a graph straight line from origin, so the slope of this graph is nothing but TA by V infinity, that is TR as TA is same. So we have to minimize this slope of this graph. The slope of this graph is minimized when it is tangent to this curve. So the point at where it intersects that graph and the velocity at that point will give you the maximum range. So if you do the math, and as explained during the Bre-GAY derivations, so at this point your CL to the power 0.5 by CD should be maximum. It will give you the maximum range for a jet powered aircraft. So the velocity at which if you want to fly is, this should be maximum, this term should be maximum. That velocity will give you the maximum range for a jet powered aircraft. So to summarize, like all the four concepts of optimization for range and endurance for propeller and jet. So for maximum endurance for a propeller driven aircraft, your velocity should be such a way that your CL power 1.5 by CD is maximum. And for maximum range for the same propeller aircraft, your CL by CD should be maximum. You have to fly at that velocity, then only you will get the maximum range and maximum endurance. So for jet, your velocity should be equal to, velocity should match the CL by CD condition. For what CL by CD, for what velocity your CL by CD is maximum, that velocity you should fly. And for the jet, for the maximum range, this is called Carson speed, and this should be CL to the power 0.5 by CD, as I already mentioned. So to just compare, velocity for maximum endurance will be less than velocity of range, which you can see in this graph also. This graph, it corresponds to velocity for maximum endurance, and this is for the maximum range. So this is the summary of it. So the next part will be explained by Ashish.
Good afternoon, Ashish here. So my teammate Shri explained graphically how do we obtain for a turbojet, what is the optimum speed for maximum range. Now let's have a look at it analytically. So as you can see here, for the propeller, the range equation, the Bre-GAY range equation is consisting of the efficiency term and the CP term, which is the specific fuel consumption. There is no velocity term, which gets cancelled out. So whereas for a jet, you can see the range equation, there is a V term. So mathematically, this V term is what pushes for having a better range, you need to have a more velocity. So till now we discussed, we have assumed one important thing, and that is that CT is constant. Is it constant? So no, actually CT is not constant. The thrust specific fuel consumption actually, as you see in this graph, as the speed of the aircraft increases, your thrust specific fuel consumption increases. So from the earlier, everyone has told velocity, you increase the velocity for a jet, the range will increase, but you have an contrasting parameter, the thrust specific fuel consumption, and it is based on the fact that the jet is based on the Brayton cycle. So the engine cycle efficiency is dependent upon the delta T. Your turbine inlet temperature is fixed. You can't go beyond that because the turbine will melt, the turbine blades will melt. So that's why, and because as the speed increases, your stagnation temperature of the air increases, and therefore you have a limiting contrasting factor. And that's why what we see is that jets, the commercial airliners, typically fly 3 to 4% less than what is the optimum speed, which is the Carson speed.
Now, as we have seen, aircraft do not fly efficiently at all times. So the optimum velocity matters for maximum endurance and maximum range. It also depends on the type of aircraft or propulsion. So let's have a real picture about how the optimal velocity for different aircrafts is in real life for maximum range and maximum endurance. For Cessna 172, for maximum range, we have optimal velocity around 200 km per hour, and for endurance, it is for about 150. For turbo propeller, we have ATR 72, and for maximum range, its velocity is around 500 km per hour, and for endurance, it is about 400 km per hour. And for turbofan, let's talk about Boeing 737. For a maximum range, the velocity is around 850 to 900 km per hour, and for endurance, it is about 450 km per hour. And as we go for like turbojet, it is generally used in supersonic. So for their missions, like it can increase. It is very high. It's like around 2000 something for maximum range. Now here, as we can see, the airline is optimized at Mach 0.78, like 0.8 to 0.9. To increase it, what can we do? So here we can use scimitar blades, which is like little swept back and turned. Due to this, we can achieve Mach 0.8, and we have also observed that the SFC is also reduced. Now, but the only drawback is that it has noise problem. Now I would like to call Sanket for further. Thank you.
Hello everyone, my name is Sanket, and I will be telling like why jets climb to the stratosphere. What happens is that in a jetliner, first as the altitude is increasing, the density starts to decrease, because of which the drag as it is it proportional to the density, the drag starts to decrease, and hence my energy which is being wasted actually lowers. Second thing which happens that as I am going higher in the sky, my temperature is actually decreasing. What happens is that my engine actually works on the Brayton cycle. This is like a Brayton cycle diagram, removing the losses and all. So what happens is that this is my T inlet temperature and this is my turbine inlet temperature. The efficiency of Brayton cycle is actually equal to 1 minus 1 upon Rp to the power gamma minus 1 over gamma. Rp is the pressure ratio. What happens, to increase my performance, I want to increase the pressure ratio. But if I increase the pressure ratio, my turbine inlet temperature is actually fixed. And increasing the pressure ratio is actually increasing the turbine inlet temperature, because of which the turbine is getting damaged. But there is another way. What if I start from here? This is at a lower temperature, and this is achieved when we go to the stratosphere, because the inlet temperature is low, the pressure is low. Hence I can actually increase the Rp without changing the turbine inlet temperature. Second, after this, that at higher altitude, I can actually fly faster. Why is this so? Because in a cruise speed, the thrust is equivalent to the weight. And what is thrust? The thrust is proportional to density multiplied by V0 square. And as I said that the density is decreasing. So now to keep the weight balance, what I will do is I will increase the V0. But what happens when I increase the V0? There is another efficiency which is known as propulsion efficiency. And propulsion efficiency is 2 over 1 upon VE by V0. As I am going above, my V0 is increasing, and hence my denominator is starting to decrease, because of which my propulsion efficiency is increasing. But one thing which is coming in our mind is that is V0 constant? The answer is no, because as I am flying through the skies, my W is decreasing because the fuel in the jet is actually decreasing. And hence to calculate V0, what I will do is I will introduce the concept of cost index. What is cost index? It is the ratio of time cost divided by fuel cost. Time cost is like the time which involves the flight time, the crew maintenance time, the pilot charges, and the fuel cost is like the fuel consumed per kg. The cost of fuel consumed per kg. So although it is a constant parameter which is actually defined by the airlines, or which is defined by the airline based on their use case. Suppose the cost index is very low, which means the fuel cost is very high. If the fuel cost is very high, I will try to fly slow and burn less fuel as possible. If cost index is very high, which means that my time cost is very high. Like my time is very precious to me, and hence it is used. And in such cases, I will try to go as fast as possible, which is used in private jets. Then this cost index is actually fed to the FMS, the flight management system, and hence it will give me the climb time or the climbing speed, my cruise speed, and my descent profile. And hence I can optimize the cost based on my CI. But actually cost index can change based on different parameters, such as the weather at that location, the ATC requirements, or suppose is there any emergency like medical emergency on an aircraft. So this was from our side. like first you should know while calculating like what is are you dealing in power as in case of propeller, or you are dealing with thrust as in case of jet engine. The V factor, while the Breguet's equation was derived, we found out that there is a velocity multiplication in the terms. So it was found out that while flying 32% more, we can actually increase the performance or reduce the cost of the engines. And like we can see that while flying a jet slow is actually uneconomical. So fly a jet faster or fly it at higher altitudes. Thank you.
Questions from the audience?
Yes, please. If aircraft is flying around 40,000, 50,000 feet, and it's have a velocity, let's say Mach 2. So, and also, so first question is, if it is Mach 2, it's have a lower air density. So, what type of modification they have done for the turbojet? And the second question is, we know that drag is increasing with respect to velocity. So, why your range is not decreasing above Mach 1, Mach 2, and so on.
What was the first question again?
Confused.
If aircraft speed is
I
above
think
Mach
I
2,
think even I got confused.
yeah, aircraft is flying at 40,000, 50,000 feet. It has a speed, let's say Mach 2. As you already told that air at that altitude, air has a lesser density. So what type of modification we have to done in a turbojet engine so that it will create the same amount of power, the thrust, the required thrust? And second question, you
Leave it to the discussions later. Leave it to the discussion later.
Past 20 minutes. We are past 20 minutes.
Excuse me. We are past 20 minutes. You can count it out.
Thank you.
Thank you. So after plane enthusiast called Campbell Morris. I don't know if you have heard of him or not. He has made. Huh? He is just a paper plane enthusiast. Take a simple paper and make kind of a space shuttle bomber that which lands like swoops and lands, or that it does a beautiful turn. About 20-25 of them he has designed, and I'm sure all of them are wonders and wonders. So till now I had some demos from my own thought process in my mind, but I think if there is a guideline available, why not to go with the guideline as well as the ones which is related to the topic, right? Okay. So today's topic is range and endurance. Now, last time the ones that you saw were all simple principles of flight with a paper. Paper can also fly, as well as some bit of stability and some bit of induced drag reduction. Today I am looking at, let's say, range, right? You can throw a stone with enough power and it goes that far. But beyond that, if it is able to go, that is what we will look at as range. If I simply throw a chopstick, it is the mass-based acceleration. But here, in this case, it is this glider is called as long-range glider by Campbell and Morris.
Can do this way.
No, that space is not. In fact, I tried it in the down ground. It goes to the other end of it also.
Oh.
So it's quite really fancy. You will have to really.
Wait.
It's a completely unique fold plus a bit of a CG variation that you can see in the tape. Okay?
Go ahead.
I think I'll discontinue. Yeah. What I was telling was, sir, that there is a hobby paper plane maker called as Campbell Morris. I long ago had collected his book on I'll show it at the end of the class. He has about 30 odd models that is prepared, not only for range, endurance, maneuver, space shuttle, landing, different types of landing, and so on and so forth. Advanced planes and normal planes. So today I'm out of which now I will select. I have got enough demos to make. I think I have got a space shuttle also, so we will reach space also. So I have enough material to show at least one demo per class for their individual topic of that day. Today is range and endurance, so I have two models in my hand with me. One is the range. This is called long range glider. So if one can, in fact, it's pretty easy to make. It's about 10 minutes that it took. I think this is the longest that, one can. I hope I really was able to succeed in it. Anyway, it is supposed to go really at a long range. Next is endurance. In this case, you can easily know that I have given the winglets. I have given a dihedral. So anhedral, dihedral, I think. Which one is it? Dihedral. Okay, dihedral. It's supposed to be thrown vertically up. It really takes off, and here space is not enough. To try these two gliders, in fact, I tried it at the our auditor Niche where they fly.
Yeah.
So I've tried both of them. It reaches the other end. So our class is not sufficient, I suppose, for the space is not sufficient for the. Yeah. After the class, we can go and try. It does really fly very well, and I have given winglets and a dihedral. So. Just principles to know.
Good. Awesome. Thank you.
First thing. You ready?
Our topic is on explaining range and endurance in terms of power available and the power required. And okay, we have in the past few days we have seen this equation multiple times. These are very important for range and endurance, but we won't be deriving it here. What is power required? Power required is the power needed by an aircraft to overcome the aerodynamic drag and maintain a steady and level flight. It can be mathematically expressed as a drag into velocity. And power available is the power of the engine system it is a power delivered by the engine system to the aircraft. It can be mathematically represented as thrust into velocity, and it depends on the engine type, whether it is a propeller or a jet, and on engine operating conditions. This is a capability of an aircraft, unlike the power required, which is a dynamic demand. Okay, let's see how to derive the power required formula. First, the assumption here is the steady and level flight and low level speed. See, this drag polar equation, we get from this low level speed as assumptions. And many team has already explained this drag polar, how they came. Let's just use this equation. From steady and level flight assumption, we know that lift is equal to weight. So from that, we can get an expression for CL square. And drag is equal to, we know the drag is equal to 1/2 rho v square into CD. When we substitute this drag polar and the CL square into this drag equation, we get the equation of this form. Here you can observe that except velocity, everything is a constant. I mean, if you consider these assumptions, rho, CD naught square, K, rho, yes, every other thing except the velocity is a constant. So we can express it as in this simple form, AV square by AV square plus B by V square. So the power required, we already defined power required as drag into velocity. So with this equation, we just multiply the term V and we get this simple form AV cube by B by V, where A is 1/2 rho CD naught and B is equal to 4K W square by rho S. Yes, thank you.
I'm missing an S in the A.
So to understand further about how what is the optimal speed for maximum endurance and range, I would like to explain about the power required curve and how we obtain it. So we start off with the variation of drag with speed. Like
the graph shows parasitic drag increases, has a square relation with the velocity, whereas induced drag has an inverse square relation with velocity, and total drag, which is the sum of both, has a U-type curve with a minimum the minimum drag at this particular flight speed. So from that we know that like my teammate Vishal had already explained that drag times velocity would give the power required. So if we do this, we get that curve, which is again similar to U-shaped curve. So we can notice, however, that the minimum drag speed and the minimum power required speed is not the same. It's different because power required has a different has a cubic relation with velocity, whereas this has a quadratic relation with velocity. So now I have shown two graphs to explain how power available varies with the engine type. So we notice that for jet engines, the thrust is constant. So since the thrust is constant, the power which is thrust into velocity would vary linearly with velocity. Whereas in case of propeller engines, the power available is almost constant, since it depends on the motor, it depends on the rating rather than the rather than the velocity itself. So it remains approximately constant. So combining these both, we get power required versus power and power available graph, which we have plotted power required and power available with the speed. So I would like to mention a few things about this graph itself. So we can notice that below this particular point, below the minimum power speed point, it operates in reverse command, which is as we give power to the aircraft, the velocity decreases. So we can say that this is a reverse command region. And we can also notice that the vertical distance between the power available and power required graph represent excess power, which has already been covered by another team. So and regarding the minimum level flight speed and the maximum level flight speed, in the minimum level, the flight speed is limited by stall, whereas in the maximum level, we see that there's intersection of power available and power required graph, and that explains the maximum level flight speed. So my friends would continue about the endurance and range.
Hello everyone, I'm Bala and I'm going to speak up the condition required for optimal speed for obtaining maximum range. The important condition for obtaining optimum range is that power required should be minimum and the fuel consumption per distance covered should be minimum as possible. So one won't take that the optimal velocity would be the minimum of the power required, but it's actually not the case, because as velocity is high, the distance traveled would be more and the fuel consumption per distance will be not minimum, and so it's not optimal. To get the optimal condition for speed, according to Breguet's range equation, we can see that range will be max when CL by CD is max. That is, the drag should be minimum. So now I will tell how it's related to the power required of the from power required. We know that range is equal to speed into endurance, and endurance can be given by fuel rate per pressure power required. So we can say that range is directly proportional to fuel velocity by power required. So you can say that range will be maximum when the V by PR is max. But we also know that power required is equal to drag into velocity, which we can, from here we can say velocity by PR is equal to 1 by D. So when the drag is minimum, this term will be like minimum, and pressure power range will be maximum. This is a condition that I was told you before. Like, for optimization, we need power required and velocity should be minimum. We can say that this is nothing but the slope in the PR by velocity graph. So to make this minimum, we should try to find a slope that is minimum. So if we draw a slope from origin to in this graph and try to locate the minimum slope, we will find that the slope is nothing but the point from origin to the tangent of the power required curve. This point correspond to the CL by CD max, which correspond to the optimal velocity that is required for maximum range. This can be shown in the graph. Thanks. Now Veli will tell about the endurance part of.
Thank you, Bala. Good afternoon. I'm Edil. So let's dive into the endurance part now. So consider an aircraft maintaining a steady and level flight. We know that in a steady and level flight, the lift balances the weight as well as the drag is balanced by the thrust. So this thrust which balances the drag is the thrust required. So this is the curve, typical curve for an aircraft, which gives the thrust required with the different velocities. So diving into equations, the power required is given by thrust required times velocity, which in terms is drag times velocity. We can rewrite drag in terms of weight and CD and CL. And from steady and level flight, we know that equation of free stream velocity. So overall, we can say that power required we can write in terms of CD, CL, free stream density, and the plane form area as well as the weight of an aircraft. So this power required is hugely affected by these factors, and CL power 3 by 2 by CD plays the main part. So in order to operate an aircraft at a minimum power required condition, it is ideal to maintain the CL power 3 by 2 by CD at a maximum. So this is the corresponding graph which depicts the power required for a flight with respect to velocity. So we might have come across these equations, the endurance for a propeller driven aircraft as well as a jet propelled aircraft. So considering a propeller driven aircraft, the endurance is directly proportional to the CL power 3 by 2 by CD. So in order to maximize the endurance, it is advised to operate the aircraft at the velocity corresponding to the minimum power condition. So thus we can achieve a maximum endurance when we operate at the minimum power required condition. And in this graph, different velocity corresponding to CL power 3 by 2, CL power 1 by 2, and CL with respect to CD is given. So CL by CD max corresponds to the minimum drag condition, whereas CL power 3 by 2 by CD and that velocity corresponds to the minimum power condition. So for a jet propelled aircraft, from this equation it is very obvious that if you operate at CL by CD maximum condition, that is minimum drag condition, we can attain the maximum endurance. Whereas for a propeller driven aircraft, if we operate at a velocity corresponding to this condition, we can get the maximum endurance. So this endurance is mainly important for those aircrafts which are usually doing surveillance like U2 and then spy drones like that. So thank you.
So I'll be talking about effect of weight on the power required curve. So if I carry a more amount of fuel, I'll have a long range by the Breguet range equation. But when the weight changes, I need to correctly account that I need to adjust my velocity in order to fly at the optimum condition. So if my power required is directly proportional to the cube of 3 by 2 of weight. So if my weight increases by twice and the power required will go by 2.8 times. So thereby the velocity also has to be adjusted. So in order to fly at a maximum range from Breguet range equation, I have to fly at the V infinity times L by D max. So L by D is independent of weight, but velocity will be. So let's take if my weight of an aircraft is higher, so I have to increase, I cannot change the angle of attack since L by D will change if angle of attack change. So thereby I have to increase the velocity. So which you can also see when the weight increases, my optimum velocity will goes higher. And vice versa for the case when the weight reduces, my optimum velocity will also reduce. So thus conclusion for maximum endurance, we need to have a minimum fuel consumption. So which is from the power required curve as already explained, it will be the minimum power point.
For a jet engine, the minimum fuel consumption point will be the minimum drag point. For maximum range, the flight condition must be provided for maximum speed per fuel flow rate. So for the piston engine, it will be the L/D max, which is a minimum drag point. And for jet engine, it will be the minimum drag to velocity ratio. So that's a DR.
2.5 minutes is nice.
Okay. Any questions from the audience? So your team name is Blackbird, this SR-71. What's special about it, and is that covered in your talk here? Because you're talking about propeller-driven engines and also jet engines. What kind of an engine does the Blackbird have?
The Blackbird has a turbo ramjet engine. So it used the Pratt & Whitney J58 engine to be precise.
Good.
And
Okay.
it is
So
a turbo ramjet engine.
Is the derivation you have done for jet engine still valid for the ramjet phase of the turbo ramjet?
No.
What is the primary difference between the ramjet and the turbo ramjet? Because this is the only probably third and probably fourth presentations where we will have opportunity to discuss the propulsion aspects. So, whereas all the other three aspects, especially aerodynamics, will be covering in great detail throughout. So, just wanted to know.
Difference between turbo ramjet and ramjet is like the turbo ramjet uses the ram effect to compress the incoming air. So the SR-71 generally flies at a Mach number of 3 and a maximum of Mach number of 3.3. So the ram effect is used to compress the air, whereas further downstream of the inlet, the turbines are used, and from there it is like the regular turbojet engine.
Okay. Ramjet, you don't have the turbine. So
Yes, sir. Yes, sir. In
the
ramjet, we
turbojet
don't
is essentially required to get to a certain speed because the ramjet wouldn't even work at low speeds.
Yes, sir. Yes.
So you have to get to a particular minimum speed for which the turbojet is used, and then
Yes.
it
From there.
gets to the ramjet.
Yes.
Portion.
As ramming effect is not
Correct,
efficient,
right.
way less than Mach 1 or like that. So it is efficient at it has a speed spot between Mach 1.5 to 3, I would say.
Okay, it's good that you derived a lot of things. So I just was wondering which particular aspect might change going from a turbojet to a ramjet. Can you speculate on that? Yeah.
We can actually use the range equation for the ramjet also, but the SFCs and the thrust, we know the properties, we can use those.
No, it's a question of which aspects change. That's what I'm trying to get to. Yeah.
It's if you know SFC, because SFC obviously change. And if you know
Like,
thrust, amount of thrust produced, then you can calculate power and velocity also will be known. So we can usually not be accurate, but we can use the equations just for at least for the stability.
Yeah. See, the very definition of either the specific fuel consumption or thrust specific fuel consumption in this particular case is that you are doing a dimensional analysis to get the thrust as a function of all the parameters that it depends upon. And then you're getting a particular constant of proportionality, which is what we call as a TSFC. Right? The question is how that TSFC itself might depend on varying conditions. Here, you're not having a compressor, but what you're having is the change in the cross-sectional area, which is offering a certain level of reduction in speeds and increase in the pressure. Okay. So the levels of pressure and speeds that are there will determine, depending on, of course, again, the fuel chemistry, what is the TSFC that you're going to get. You're right. That's essentially what it boils down to. Whereas the overall behavior in terms of the aerodynamics or the dependence on L/D, velocity, etc., remains the same. Glad you brought it to that focus. Thank you. You had any question?
I just wanted to say one piece.
Yeah.
From the experience point of view,
yeah, please.
From the experience point of view, if a fuel leaks, we will not let it fly.
Right. Obviously. Right.
So he is definitely wrong. Fuel will not leak. There would be some other mechanism which probably he thinks fuel is leaking, or there would be probably some other air channels which may have been diverted. I don't know where has he seen the photograph of it. Yeah, he must have seen it. And now, have you seen a literature in which somebody has quoted it leaks? Please don't mess it. Please don't be serious, because if fuel leaks, it is a clear indication of a crash. It can't sustain. The engine temperature, body temperature itself is more than 70-80 degrees centigrade. The surrounding fuselage, which is holding onto the wing, that itself is about 70, 80. You are talking about fuel. It is ATF. So I don't know how. I mean, I don't know. I don't want to comment on you. But please find the literature which says that it leaks, and then come to conclusion. If you have seen a video, no. If you, it may be a
I'm
video.
not aware of it, so I think we should probably check the source to see its reliability, and then we can see it. We can comment on it.
Good afternoon, everyone. Good afternoon, sir. So, for today, our topic is how atmospheric affects aircraft performance, particularly range and endurance. So, previous teams have covered a lot of how different things actually determine range and endurance, mathematical derivations and all. But one of the principal things that actually allows us to generate lift or travel in the is basically atmosphere, right? So we need to understand how atmospheric effects affect our design. So this is the fundamental equilibrium condition for an aircraft.
You can click on view and full screen.
कौन सा होता है? So it's a simple at cruise. This is what we want. Like the lift should be totally equal to weight and thrust should be equal to drag. And for that, our velocity comes into picture. So as you can see over here, our velocity is a function of density. And density directly affects on the atmosphere. As we actually go above in the atmosphere, density decreases. That means our velocity should increase to maintain the same amount of lift. And this density velocity coupling is the fundamental mechanism that drives the altitude performance. Then we'll look at some standard atmosphere models. As you can see over here, this is our atmosphere. This is the troposphere and this is the stratosphere. This is the tropopause region. As you can see over here, it is somewhere around 30,000 feet. That is when tropopause begins. Generally, all the cruise flights actually fly above the tropopause. The reason being very simple. As you can see over here, the temperature from here to here decreases. But as soon as it reaches over there, it becomes constant. The pressure as well. The reduction in pressure is very high in the troposphere. But once it goes above troposphere, in the tropopause region, the curve gets more steeper. Same goes with density. So that is the reason generally commercial flights prefer to fly in the tropopause region. This is what you can see is the relation between temperature in the troposphere region. As you can see, as the height increases, our temperature reduces. I think the graph over here is a bit wrong. Negative should be here. The temperature should reduce.
Minus 50 degrees centigrade sea level.
It's 50 minus 57 degrees Celsius here and 15 degrees Celsius on the other side. Right. It did a mistake while generating the graphs. I think same should be with the pressure as well. It's also flipped, the pressure as well. And density as well. So let us go into that is one of the standard atmosphere, right? But the standard atmosphere actually designed for this climate.
Different planet, angels, right?
It's temperate. Latitude. It's from it's particularly standard atmosphere works based in latitude from 30 to 60 degrees. For this latitudes, that is our tropical and polar latitudes, we need a different kind of atmospheric model that particularly looks into those things. So as you can see over here, this is our tropical, this is IISc standard atmosphere. It assumes 15 degrees Celsius at sea level temperature, and it becomes minus 2 degrees Celsius at 1000 feet. But as you can see over here, our tropical, which is much more related to India, it is 27 degrees Celsius sea level, which is much more accurate. And this is a polar, which is basically minus 15 degrees Celsius at sea level. And since as the temperature increases, there's lower density, so this will give worse performance, whereas this will give a better performance. And then there's if you want to change from one atmospheric model to other one, there's this relation. Now I'll talk about the density altitude. So what happens when a aircraft goes, this is a general for an aircraft. It's takeoff, it's cruise, it's landing, and descent. So as you can see over here in this region, until it reaches that, what you can say, cruise altitude, 40,000 feet or 12 kilometers. This particular region, the density change is very drastic over there. So for that, in order for us to measure everything, we don't measure density differently or temperature differently. What we do is we combine them into one parameter, and that is density altitude. So what density altitude tells us is what will be what will the altitude result. For example, right now we are flying at 5,430 feet. But if for a higher temperature, what it would feel like, that is what density altitude tells us. For density altitude, it will be 8,500 feet. So we have to adjust our performance accordingly. So as a pilot, we don't have much things in control, right? We have only three things. One is throttle, that is m dot of fuel. Then second thing is RPM of the engine. And the third thing is control surfaces. That makes elevator, aileron, and rudder. These are the only three things we can control. And these three things depend completely on how our atmospheric conditions are outside. So density altitudes gives us a way to actually, instead of calculating all the other things, if we know the density altitude, we can fix all these three things in one go. Next, this is a density shift in indicated airspeed versus true airspeed. As we can see over here, at sea level, the density at sea level, we will require this velocity to get this particular thrust or that drag. But at the same time, at flight level 350, that basically means 35,000 feet, we will require a higher velocity to achieve the same level of thrust. That is what determines the true speed, airspeed, and indicated airspeed. True airspeed is an airspeed which is at which the aircraft is flying, and indicated airspeed is what you can say. It's relative to what at the sea level. That will go into true indicated and indicated pressure. So as you can see over here, true altitude is the geometric altitude, like directly calculated from the sea level at which we are flying. Let's say indicated altitude, it's like what the pitot tube is seeing right now. So it will be based according to what is the density of the air outside. Whereas what we actually need is pressure altitude. Once pressure altitude is calculated based on 29.92 inch of mercury. That is basically 760 mmHg, right, in metric units. So this is what we use for performance calculations. The reason being, like, once we go to cruise altitude, here we calculate density altitude. But once we go here, we need basically pressure altitude, because all other factors doesn't matter that much. Temperature doesn't matter that much. Density doesn't affect us much. Nor does humidity. What affects us more is pressure. Pressure is the only thing which varies huge over those altitudes. So what we need is a relation between pressure altitude, comparing it with the sea level one, for which we have designed all the systems. So once we go to we calculate the pressure altitude, we will be able to optimize all our controls accordingly in order to ensure a steady cruise. Next, I will go into different kinds of speed. Basically, indicated airspeed, calibrated airspeed, equivalent airspeed, and true airspeed. Like, what is the difference between all? Indicated airspeed is simple. It is like what is indicated on the reading. Like if you are flying at a current away, whatever the instrument is measuring is the indicated airspeed. Calibrated, if you are calibrating it for any kind of correction, that will make it CAS. So for most of the instruments, IIS will be equal to CAS. If we bring it in the compressibility correction, then it will become equivalent airspeed. And if we bring it the density correction, then we will get what is the true airspeed of the aircraft. So as you can see over here, how true airspeed and indicated airspeed different diverges with velocity. So at next, we'll go into some aerodynamic fundamentals. So as we can see over here, this is the equation of our drag. This is our skin friction drag, and this is the induced drag. And as you can see over here, as the airspeed increases, or induced drag basically decreases and becomes constant. Whereas as airspeed increases, parasitic drag increases. Because as we go above in the atmosphere, our density basically decreases. So that basically reduces our drag. Because as you can see over here, induced drag is directly proportional to density, inversely proportional to density. Whereas parasitic drag is directly proportional, so it increases. So what we are actually trying to optimize is find the optimum position where we can actually run our aircraft, and that is where is the position at which we will get maximum aerodynamic efficiency. Next is a difference between propeller versus jet aircrafts. So this is a propeller aircraft. As we can see, for a propeller aircraft, if we derive propeller aircraft is generally a power minimization problem, finding the optimum range, maximum range and maximum endurance for propeller aircraft. Because for propeller aircraft, what happens is what the fuel does, it converts chemical energy into electrical energy, and that is used to turn this shaft, which will be the fan, which will be turning the air and producing the thrust for us. So what we need here is the power that is here, that is the putting on the shaft. And if we minimize that power, we'll get the maximum endurance. And for maximum range, the ratio will be something like CL to the power 3 by 2 by CD. And for maximum endurance, it will be CL by CD. Next, for jet aircraft, jet aircraft is basically runs on thrust, right? For jet aircraft, it doesn't matter. The chemical energy is directly converted into thrust. The chemical energy is directly used to propel the air. It's mixed the fuel, and that is expanded through the turbine, which basically runs our shaft, which runs our compressor, and that is then converted. So for jet aircraft, what if we maximize the thrust, we'll get the maximum range. That will be at CL to the power half by CD, and the maximum endurance will be at L by D max. Then how altitude shifts our velocity. That is what I want to show here. As you can see over here, this is our thrust required curve at sea level. But at FL equal to 400, it will go above what is the thrust that we can generate, the optimum. So we can't fly above this altitude, right? Because we won't be able to generate that much amount of thrust. As we know, drag reduces with density, and engine efficiency also increases because lower temperature is found at higher altitude. So that is the reason that intersection points moves at a higher speed. Next, the density shift, and this is also similar to that. As the air thins, the speed we require actually increases. So that is, we can see density shift, drag shift. Basically, the velocity required increases, and the drag requires increases as well at higher altitudes. Next, I will ask my teammate.
What exactly do the FL ratings mean? FL 350?
FL means basically flight level. It is the
Flight
altitude
level.
at which the aircraft is flying. So, for example, FL 350 basically means it is flying at 35,000 feet.
Okay.
Good afternoon, everyone. My name is Ravi Agrawal, and in the beginning, I will show some results that has been discussed in the earlier presentations, and then I will continue with the atmosphere contributions. So, as we have seen earlier, the maximum range for the propeller depends, like for maximum endurance, we need to fly at the minimum power, but for the maximum range, we need to fly at higher power to maximize this quantity of CL. And but for maximum endurance in for maximum endurance, in propeller we need to fly at this minimum power, and in jet we need to fly at for maximum endurance we need to minimize the L/D ratio in jet, and in propeller we need to minimize the power for maximum endurance. And we have already seen this the derivation of the Bre-GAY equation, which consists of the three terms. One is the propulsive efficiency, second is aerodynamic efficiency, and third is the fuel fraction. So as we know, the velocity is dependent on density, and specific thrust is dependent on temperature, and aerodynamic efficiency is also dependent on compressibility. So here the atmosphere will play its role in affecting the range and endurance. So as the altitude increases, we can see that the airspeed at which the optimal, as the altitude is changing, the optimal airspeed is also changing. Like for this sea level altitude, the optimal airspeed is this, but for 250 altitude, the optimal airspeed is changing, and it's also changing the specific fuel consumption, specific range. So as also since the altitude is increasing, the available thrust is decreasing, and the cruise window, aerodynamic efficiency is increasing. So this is the optimal window where the aircraft should fly in altitude. And this is the effect of temperature, or the temperature of the day on the atmosphere. On the colder day, the density is slightly higher, so the thrust required is higher, and the range gets increased. On a hot day, the density decreases, so the thrust required gets decreased, and so the range decreases. So this is since the day is hot, the thrust required gets there is a thrust loss, because density is inversely proportional to temperature, and we need there gets a ceiling penalty, we need to fly at this height because of this. So this is a normal, we are flying at this velocity, and this is the wind velocity. So our net velocity becomes this, and which affects our performance, because if there is a tailwind, when there is no wind, if we need this much power, so at tailwind the power gets increased, and also in headwind the power also gets increased, because we need to maintain the lift. So when there is a tailwind, we need to decrease our velocity, so that also increases our power consumption. And here's the effect of humidity. As we can see, H2O molecules has larger size and lesser weight. So in the same volume, there is lesser weight, so the density is less with higher humidity. So the humidity also affects the density, and we have already seen the effects of density on the range and endurance. So humidity in the atmosphere also plays its role. And this is the coffin's corner, where we cannot fly in this range, else we will stall, and we cannot fly in this range, else we will have the shock on our aircraft. So we need to fly in this range, and that is the corner where we need to avoid to go there. So this is the range where we can fly in, domain. And from there my teammate will continue.
Okay, so now here I will talk about how practically airplanes basically use the altitude. So the lower graph is the ideal cruise climb, which is actually ideally used by aircraft as their weight decreases due to fuel consumption. So as the aircraft consumes fuel over time, its weight decreases significantly over the flight duration. So this is the ideal cruise climb. So as you can see on the right side, the schematic. So as weight drops, my lift also drops, because lift is required for the weight to go up. And as lift drops, we can go at a higher altitude to maintain the same lift. So density will drop with higher altitude, so we can climb. So the upper graph, which looks like a step, is basically the basically the path which the flights take, because of the ATC allowances. So it's basically like a step.
So this is the case study for the transatlantic crossing. So flight A is the fixed flight level 310 where they don't change the height once it's airborne, and the second flight B is the optimized flight level 390 plus step climbs, where as we have seen in the last graph there is a step climb. So in the second case, the fuel used is less as compared to the first case. So it leads to savings in terms of cost and CO2 emissions. So coming to engine performance. So this is the TSFC versus altitude curve. So the TSFC has a minima at around FL390, where we're just above the tropopause. Above that, low density reduces the mass flow rate, while below that we have hotter air, due to which like our thermodynamic cycle efficiency is lower. So at around FL400, both these advantages and limitations lead to the lower TSFC point. So as a result, most airlines try to fly at that altitude. So mostly airliners try to look at the cost index. So cost index is basically the time cost versus the fuel cost. So for maximum range, we basically go for minimum fuel and maximum time when the cost index is 0, while for maximum speed we burn the most fuel so that we reach in minimum time. So for that the cost index is 999, for example. The optimal operation happens at around cost index around 50. Number is not given here. So most airliners try to keep the cost index curve at around 50. When there are headwinds, for example, we try to increase the speed. So as a result, then the fuel cost increases. Sorry, the time cost decreases. So CI decreases. While for tailwinds, we try to increase the time. So then the reverse happens. So this is the cost analysis. So airliners try to minimize the total cost. So as my speed increases, the time dependent cost decreases while the fuel cost increases. So at around max 0.7, we get the most economical speed, for which the direct operating cost is the minimum. So this is the practical flight workflow, which is solved iteratively before every flight. So these are the inputs. They look into the winds, the temperature deviation, and the weight of the aircraft, and they get the density, as you have seen in the earlier slides, how density affects the flight. Then you have to check the compressibility and also apply the cost index, like the cost matters and everything. And the output gives us the flight level and the speed at which we want to operate the flight. So this is the conclusion. So these are the atmospheric effects, density, temperature, and wind, which basically affect the aerodynamics, L by D ratio, the thrust requirement and the drag, and dictates our performance in terms of range, speed, and endurance. So the last thing which I want to say is that performance is not a static number. It's basically a continuous solution to the dynamic atmospheric equation, which changes over time. Thank you.
Questions from the audience?
If you could have reduced what others would have covered and derivations, you had quite a bit of information in terms of how atmosphere affects the performance and the range and endurance.
Yeah.
I think you could have more focused and you could have finished it in 15 minutes, but you could have covered everything else. I think you simply wasted time.
We're sorry for that.
Nothing.
Yeah, once again, you are having lots of focus slides, which is very good. Glad you moved on from Perplexity to NotebookLM. But when you're using these, you have to also be careful about their hallucination, which is what that curve with the altitude of the pressure, density, etc. show. That is one thing we discovered as we go, but I think you should do your homework in terms of looking through them very carefully and seeing there are no issues. Because we may have identified one issue, there might be many other issues which we have not identified as well. So just be a little more careful. I encourage you to continue using these tools, but with a pinch of salt. You ensure that there are no errors coming, especially when you're presenting it to a large group like this. Okay. One of the things you mentioned was that the pressure is more important than the density. I couldn't follow the argument that your logic behind what you are saying there.
I mean, once we reach the cruising altitude, Here what we want to find is here our temperature changes drastically, so does our density and our humidity. So using this, what we calculate is density altitude, and this is what we use to actually make the basically find the optimal speed. And basically optimal speed basically means optimal control, optimal mass flow rate for fuel, and optimal throttle, and optimal RPM, so that we can ensure a particular thrust, optimal speed for to ensure our climb. But once we reach over this atmosphere, here actually our temperature reaches a constant. Temperature becomes constant. Humidity also does not. It has a very negligible effect. Humidity does not change that much. So these two things are already eliminated. So what we actually, instead of calculating density altitude and or including all these three effects, we just calculate pressure altitude based on what is the pressure in the air. So we'll find what is the true pressure over there, and then use that to find the pressure altitude. So that is the altitude that we should be flying. That's it.
Okay, but they're kind of equivalent, right? You're using an ideal gas equation, P is equal to rho RT. So if your temperature is constant, P and rho are related to each other.
Those are the two terms that are used.
Okay.
Density altitude and pressure altitude.
Sure. Okay. Yeah, I think, yeah, that's it. Thank you.
Thanks.
Taxiing cruise mission, descend, hover, or it is called flake behind land. Be careful with the terminology. Very good. The other thing I really liked is the economics. I think one of the previous presentations also went into that. Engineers usually hesitate to get into the economics aspects. But again, because you're getting the information through AI tools, you have to be a little careful in what it means. For example, you were talking about the cost per fuel, that kg, that is fine. When you're talking of the cost per time, how it is actually evaluated, you need to explore further through more prompts to understand the logic or the sources from which it is gathering information. It's very useful because it might have access to a lot of sources which we might miss out on typical searches that we do, the conventional way of searching. But at the same time, you need to explore a little further for those kinds of tidbits or interesting information to understand if the logic is valid, and then are the sources reliable, like what we talked about SR71 just some time back. So those kinds of things that if you can explore a little further and come up with something that you can be sure about, there should be some kind of clarity in whatever you present. Yeah. Thank you. Yeah.
Actually, we found the document.
Huh?
We found the document about the leaking problem.
Oh, you found it. Okay.
Actually, in NASA papers, they have mentioned it used to leak.
Okay.
The main problem is they didn't use the separate fuel tanks to reduce weight. Because let's say, inside wing, if you create a separate fuel capsule, it will add weight. So it's not that wing only used to contain the fuel. And the fuel they used was JP7, which has higher flashing point, so that it would ignite in the violation of the tarmac. And it used to leak considerable fuel while taxiing and takeoff. Once it reaches, let's say, supersonic speeds, due to aerodynamic heating, the temperature would go till 250 degrees centigrade, 50 degrees Celsius. So thermal expansion they have to consider. Otherwise, if they don't consider, so it will buckle due to the structural buckle panel. So it is mentioned in NASA paper as well as memos from Campbell, Air Force.
Were there any accidents related to that, or it was found before anything?
I think
could
there
happen?
were some accidents, but the accidents were not only related to this. There were some other causes also.
Okay.
But by design it was they didn't find any other solution, because during 1960s they were not the technology of sealants was not that advanced, which can perform well in cold -60 degree as well as till 250 degree. Now I guess there are a couple of sealants which can be used in this condition.
Thanks for clarifying that.